So last time last time I basically showed you how we can start using the signed permutation presentation of a Coxeter group to start proving properties about the group itself. We started talking about how we can tell a lot about the length function, for example. In fact, we can compute the length function directly from the signed permutation representation. And I proved this lemma last time, which is quite important, that if you have some element of the Coxeter group, which you write in some way as S1 up to Sk, and if you take some reflection T, then the following statements are equivalent. So one statement is that multiplying W by T makes it a shorter element. The second statement is that when you multiply W by T, you can rewrite that as the same exact expression, except you knock off one of the things in the expression. And the third statement is that this reflection T can be written as going from S1 up to Si and down to S1. So these three statements were equivalent. I should mention that last time I proved this for when W was reduced, but the same proof goes for when W is not reduced. The important thing, so we used the W was reduced to say that these elements were different from each other. So if you chose different i's, this element S1 up to Si and down to S1 were different. But this statement is true in general. The only thing is that now, if this expression is not reduced, then some of these guys are going to be equal to each other. But this equivalence is still true. Okay? So just wanted to remind you about that. And we're going to talk about two very important properties that Coxeter groups have. So the first one is called the exchange property. Okay. And what that says is that if you have some element W of your Coxeter group, S1 up to Sk, and you multiply it by some generator, so we take some generator. Let me put it this way. Let W be an element of the group, written in this way. S is a generator. And suppose that when you multiply W by this generator, you make W shorter. Okay? Then, I'm just going to repeat what I said here. You can obtain W by just removing one of the s's in this expression. Okay? That's called the exchange property for Coxeter groups, and you see that this is exactly the equivalence from A to B here in a special case, because B here talks about any reflection T, and when I talk about the exchange property, I'm letting, in this case, T is one of the generators, not a reflection, but a generator. And just to make sure, maybe you'll see this if you look it up in some book. Sometimes people talk about the strong exchange property, and the strong exchange property just generalizes this to reflections. Yeah.
So would this be then SW is equal to this?
Yeah, thank you. Yeah, this is exactly what I said here. Yep.
The hat on top of S sub I.
The hat means that you have the expression from S1 to Sk, and you drop the term Si. So this means this term is missing.
It's not in that expression.
Exactly. I'll keep using this notation a lot, but if you forget what it is, keep asking me. Okay? So So that's the exchange property and the strong exchange property, and we proved those last time. Okay? We'll see why this is a very important property. And then there's a related property called the deletion property. Which says the following. If you take some element of your Coxeter group and you write it as a word, and this word is not reduced, then it's a fact that you're going to be able to rewrite W as a shorter word by just removing two of the guys here. Okay. So you're going to be able to rewrite it as S1, dot, dot, dot. Then you drop term SI, you drop term SJ, and you leave everything else there. Okay. So this is saying if you have an expression for W and this expression is not reduced, then that means you can shorten it in the following way by just removing two of the letters of the word. It doesn't tell you which two, but it tells you there's some two words that you can remove and get the same element back. Okay?
Calling them words, aren't they generators?
So the SIs are generators, and whenever I write a product of generators, I'm calling that a word on the generators. So when I say word, you should think product of generators.
Okay, but the SI that you're dropping and the SJ you're dropping, they're generators.
Exactly.
They're also kind of trivial words, right? Well, not trivial, but they're words that
Yeah, sure. So we haven't proved this yet. And I'm going to prove the deletion property for you. I did prove the exchange property for you. But before I prove it, I want to show to you why this is the right statement that we should be proving. Okay? And this is thanks to an observation that Thomas made to me at the end of class last time. So let's see what these two statements say for the symmetric group. And then you'll see that these statements make perfect sense. Okay. So there you go. I walk here and magically there's a picture of some braid. This is some wiring diagram. Okay, so wiring diagram for W equals S3. The same example that I keep drawing. Okay. Now I claim that if I now multiply this, let me multiply this W by the generator S4. Okay. So what am I doing when I do that? All I'm doing is that I'm sticking S4 below here, right? So here's S4, and I go like this, like this, like this, like this, and like this. Okay. So I claim that the element S4W is shorter than the element W. And I think Thomas knows why. So why is that? One way of doing it would be to just, write this out, do the computation. It'll take a while, and you can try to write these in terms of generators in the shortest way possible. I claim that an easier way is just to stare at this diagram. Because you see, we said that the length of an element is just the smallest number of crossings that you need for the wires. Okay? What did I do by multiplying by S4 at the left? What I did is that I crossed again two wires that had already crossed here. Yeah? So let me show you that. By multiplying by S4, I introduced a crossing here of two wires that had already crossed over here. Wires 1 and 5. Yeah? Wires 1 and 5 crossed here, and then I'm making them cross again here. Well, I claim that I can shorten this word, and the way that I can do that is basically by just, if I'm going to make them cross twice, I can just uncross both crossings, and I'm going to get exactly the same wiring. Yeah? So if I just take this and make it straight here, and make it straight here, then I'm going to get the same wiring from the top to the bottom. Yeah? And I have shortened my word, because what am I doing? I'm basically getting rid of S4 and getting rid of S4, S3, S4, this S3. Okay? So that means that I can write this as S3, S4, then this S3 hat is the one that disappears. S4, S2, S3, S1. Okay? So what the exchange property is saying for the symmetric group is, if you introduce a new crossing of two wires that you already crossed, then that's silly. You might as well just not introduce this crossing and cross the two wires that had crossed before. That's what that statement says. Okay? So that's the exchange property. Any questions about it? I'll let you think about what the deletion property says then. I'm reluctant to erase this, and I'm reluctant to draw it again. So let's talk about the deletion property. So imagine that this red stuff was never introduced to this picture. Okay? So we claimed last time that this word was not reduced. We claimed that W can be written in a shorter way. And this is what Thomas pointed out to me. The reason that this can be shortened, I think now I gave you time to parse this picture. So I'm going to erase and now go to the deletion property. So forget about S4. Forget about this crossing. Forget about this. And forget about this. And let's talk about the guy that we started with. This is the guy that we started with. It's a word for some permutation. And I claim that it's shorter, that it can be shortened. It's too long, and the reason that it can be shortened is exactly the same one, that there's two wires here that are crossing twice, and that's pointless. So I forget which ones they are. 3 and 5. So here's 3 and 5. They cross. Wire 3 and wire 5 cross. And they cross again down here, right? Okay. And so what Thomas pointed out to me is that one way of shortening this word is by saying, well, let me just remove these two crossings. What am I doing then? I'm just removing S3, removing S4, and shortening my word in that way. And I get S3 is removed. Then this S4 is removed. S2, S3, S1. So again, the deletion property is saying almost the same thing. It's saying if you have a word that's too long, then you can knock off two generators.
The second S3 that's
S3,
deleted?
S4, S3, it's the S4. Yeah. Okay. So this is the intuitive picture that you should have for the exchange and the deletion properties. And like I told you, once you manage to make the correct statement for the symmetric group, if you manage to state it in the correct way for general Coxeter groups, then actually the proof is not going to be so hard. So let's question.
So, well, they'll always come in multiples of 2, right? So it could be that we could knock off 4 generators.
Right. So if this is still not reduced, so the question is that you can always reduce 2 at a time. So you can start with a word that is not reduced. Then knock off 2 generators. If that's reduced, then you're done. If it's not reduced, then you can knock off 2 others and keep doing it and keep doing it.
Is there an obvious algebraic way to do this that I'm missing?
There is no obvious algebraic way of doing this that you're missing. And this is why whenever you try to prove things algebraically with Coxeter groups, it's hard. I mean, it's not easy to know which generators to knock off. But this statement is pretty easy, actually. So I'm going to prove it, and you'll see that it's easy. But it's not going to tell me what I and j are. Okay? Maybe it will, actually. I think it will. Let's think about this proof carefully, and I think that it will tell us which are the two guys that I should remove. I think that's true. So I proved the exchange property is true. Now let's prove the deletion property using the exchange property. Okay. So take S1 up to Sk not reduced. Okay. Now, what I'm going to do then is I know that so I'm going to consider the what is it? Consider the largest I for which Si dot 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 Sk is not reduced. Okay. Why can I do this? Because I start with S1 up to Sk, which is not reduced. Then I can ask for S2 up to Sk and see if that's reduced. S3 up to Sk and see if that's reduced. And I know that the last one, Sk is reduced. So by knocking off the first guy at a time, I start from a not reduced word. I end up with a reduced word. So somewhere in between, I must have gone from being not reduced to being reduced. Okay.
Over here, that we crossed out one in the middle. Over here, we're definitely not doing that. We're getting rid of all the ones on one side, and then they end up reduced. Are we just saying, okay, whatever word it is that, completely different word, but it's reduced, so that's okay? Or are we saying that it generally will be on one side, that we take these things off and we reduce it?
So the question is, how should I understand this statement in this picture, basically? I think that's more or less your question. And the answer is that I'm taking a word that is not reduced, like this one. Okay. So this is not reduced. That means that things are crossing twice. And what I'm doing is basically saying, okay, how about this one? Is this reduced? Is this reduced? Is this reduced? And I'll go as far up as possible while not being reduced. Okay? And then I'm going to do something. Right. So in this case, actually this one is reduced. Once I get to S3, I think that's reduced. There's no double crossings here. So this is what I'm doing. Okay. Si up to Sk is not reduced. Si plus 1 up to Sk is reduced. So how can this be reduced and this not be reduced? That means that I had a word of a certain length, which when I multiplied it by Si, it didn't get longer, because if this word was longer, then, I mean, if the element Si plus 1 up to Sk was longer, then this would be a reduced word for it. So, I mean, this I'm assuming is reduced, so the length of this element is k minus I. This really is the shortest word possible. Okay. When I multiply by Si, I'm claiming this is not reduced. This is not reduced, so the length is not k minus I plus 1. Okay. But what that must mean is that the length didn't go up, it went down. In fact, let me give you a lemma here that I'll ask you to prove, which is that if you take a generator and you multiply it by a word, then what you're doing to the length is either increasing it by 1 or decreasing it by 1. Those are the only two things that can happen. Okay. I'll leave this as an exercise for you. And so what I'm saying is, when I multiply by Si, the length did not go up by 1, so it must have gone down by 1. And that means it's shorter. Okay? So multiplying Si plus 1 Sk by Si made it shorter. And that means that I can apply the exchange property, which tells me that multiplying by Si knocked off one of the generators. That's what it did. Yep. And I multiplied by Si. All I did was knock off one of these letters. This is the exchange property. Okay. And then I multiply on the left by S1 up to Si minus 1. I multiply by this. And what I get is this. Then Si is missing. Then Si plus 1 is here. I continue. Sj is missing. And Sk. And so what I get is that is exactly the statement that I wanted to make. That this word, which was not reduced, was shortened by getting rid of Si and getting rid of Sj. Okay. How should you see this in this picture? Again, you say this picture has double crossings. And so I'm going to keep going until I see the last double crossing. That means that up to here, there's double crossings, and here there's not double crossings. And what I'm saying is if here there were no double crossings, if here there were double crossings and here there weren't, that means that this guy must be one of the guys giving you trouble. So you can remove him and whoever it crossed earlier.
So in general, you can determine what I you want, but it's the J that can be a little wily.
Yeah. So this proof tells you which I you should remove, but the J comes from the exchange property. Yeah. So that proves the deletion property. Okay.
So the I, does it come from the exchange property?
The choice of I was done here. I was the first letter in the last word that is not reduced. We made that choice here. And then J came out from here, where we use the exchange property. But I should say, I mean, in general, I think I would advise you not to read into that too much, because in general, it's not clear which I and which J you can take. And in general, the way you use this in proofs is you say, well, let me take a word. If it's not reduced, then I can take two guys off. And generally, you're never going to use which those two guys are. So if you understand this statement, I think this is really the most important part. And the proof doesn't exactly tell you how to find those I and J, but you won't need to generally. Okay? So that proves that Coxeter groups have the deletion property also.
So if I'm making some computation, you hand me some word and ask me, is this reduced? Is it better to use the deletion property and try and hunt down where things are wrong, or is it better to use the relation in the group and see if I can rewrite this?
Sorry, I didn't want to erase this. How do you tell if a word is reduced or not in practice? I mean, hopefully it's the symmetric group, and then you can use the wires. But if it's not the symmetric group, then what do you do? For example, last time we found a way of computing the length of a word, or the length of an element. We said the length of an element is the number of reflections that are made negative by by the sign permutation element. So that's one way. I'm
thinking particularly like the first homework problems. You hand me some ASCII word, and I want to know if that's a reduced word. And if it's not, I want to write it as a reduced word.
Mm-hmm. So the question then is, if I give you some element of the group, how do you write as a reduced word? We'll see. We'll give you a. I mean, this somehow is equivalent to this word problem, and whether this word problem can be solved or not. And we'll get to the point where we can answer a question like this well. But so far, we're not really there yet. Now let me make a statement that is pretty amazing, and it shows you the importance of these two things. Theorem. Let's say that you have some group W, and let's say that you have some set of generators for the group. And all the generators are assumed to have order 2. Okay. So the following are equivalent. First, that what I gave you really is a Coxeter system. Second, that it has the exchange property. Third, that it has the deletion property. Theorem is due to Matsumoto. I think in 68, something like that. I think this is an amazing theorem because it tells you, okay, we just proved two things about Coxeter groups. That Coxeter groups have the exchange property and they have the deletion property. And the amazing thing is that actually these two properties, in either one of them, completely characterizes Coxeter groups. So that means that if you just find some group in the street and you ask it, do you satisfy the exchange property? If the answer is yes, that means it's a Coxeter group. Maybe this makes you wish that I had told you this before the homework was due, because you saw how hard it is to prove that something is a Coxeter group. It's hard. But here's a way to do it. Just prove the exchange property, or prove the deletion property. If you prove either one of these two, that means that you actually have a Coxeter group in your hands. Okay. Any questions about this statement? So that's the statement. But I haven't given you a proof yet. So proof, I think, maybe I'll do it next time. Okay. Because before going into this proof, what I would like to do is show to you how you actually use these two properties, this exchange property, this deletion property. I want you to get used to working with them because they are extremely important, and these two properties allow us to prove a lot of the very hard things that we haven't been able to prove. Okay. So here's some nice consequences of exchange and deletion. The first one is the following. Any word in the generators, S1 up to Sk for W. If I give you any word for W, that contains a reduced expression for W as a subword. Contains a reduced word for W as a subword. Okay. This is something that Eric already pointed out to us, and the proof is very simple. You just say, take your word. If it's reduced, then this is obviously true. If it's not reduced, then apply the deletion property. The deletion property tells you that you can express the same element W by knocking off two generators from this word. And then you ask yourself, is that reduced? If it's reduced, you're done. If not, you knock off two other generators, and you keep knocking pairs until at some point you're going to get a reduced word. So proof is fairly easy by the deletion property. Okay. Seems easy now, but if I had asked you to prove this a week ago, you would have found it very difficult. So that's one proposition. Let me keep this up just in case. You never know when you're going to need a picture like this. Can I erase this? Let's make another nice statement. Proposition. Let's suppose that you have two different reduced words. Okay. We know that you can have different reduced words for the same element. For example, in this symmetric group, we know that ABA is equal to BAB whenever A and B are consecutive generators. So you might imagine that this is ABA and this is BAB, for example. Or it could be a more complicated element and you just have two different expressions for it that are both reduced. Okay? The consequence of this is that actually the letters that you use here are the same letters that you use here. Or by letter, I mean generator. I'm not claiming that you use them the same number of times, because this could be ABA and this could be BAB, but the sets are equal. So the same letters that you use here, you use here. I think we're getting somewhere stronger. This is a pretty strong statement. So let's prove this. How does one prove something like this? Well, basically, by contradiction, let's assume that you found a generator here that you didn't find here. By contradiction, assume that you found Si, which is not one of these Si primes. Okay? And you'll see why it's going to be convenient that I'm just going to choose the smallest such I. The smallest Si that doesn't appear here. With I minimum. Okay? So let's go back to this lemma that I wrote over there. which describes to us. Sure, let me let the camera come and see what I'm doing. What does this lemma do? It says if you have an element of the group, and it has, if you have an element of the group, this lemma describes which reflections shorten the element. Okay? This doesn't depend on the word that I chose for W. This is a property of W, not of the word. And this lemma tells me that those reflections are exactly the ones of the form start at S1, go up to Si, and go down to S1. Okay? Now, there I have two different expressions for W. And this lemma is true for both of them. And what that tells me is that the words that I'm describing here, sorry, the reflections that I'm describing here are the same whether I use S's or whether I use S primes. So let me say that now. The reflections T that shorten W, by which I mean that the length of TW is less than the length of W, are S1 up to Si down to S1 for 1 less than or equal to I less than or equal to K. This is one way to describe them. And a different way to describe them is you start with S1 prime, you go up to Sj prime, and you go down to S1 prime for each j between 1 and K. Okay. I'm describing the same set in two ways by the lemma. What does this mean? This means that this element that I wrote right here, S1 up to Si and down to S1, is one of the reflections that appears in this set, and you must be able to find it here. So S1 up to Si and down to S1, you must be able to write as S1 prime, you go up to Sj prime, and you go down to S1 prime for some j. Here I'm talking about this Si. This Si is the same as this one, the first one that doesn't appear in this list, and this is just some j. I have no idea which j it is. Okay. So what does this tell me? Let's erase here. Okay, let me rewrite that here. And now let me solve for Si. Okay. How do I solve for Si? Basically by multiplying on the right by all of these guys in the correct order, and multiplying on the left by all of these guys in the correct order. Okay. So I multiply by remember, all of these guys have order 2. They're their own inverse. So I multiply by S1 on the left, and I get rid of this one. I multiply by S2 on the left, and I get rid of this one, all the way up to Si minus 1. That gets rid of all of these guys. And to get rid of all of these guys, I multiply by S1 on the right, then by S2 up to Si minus 1. I send these guys to the left, and these guys to the right, and that's the expression that I get. Okay. Now, the exact expression here doesn't matter too much. What is important is that I just managed to write Si in terms of Si primes and smaller Si's, which I know I know that each one of the smaller s's is equal to some s prime. Yeah? So that means that every letter here is equal to one of the sj primes. This is some word in the s primes. Okay. I just managed to express si, which is not one of the s primes, as something in terms of the s primes. Okay? Is that clear so far? But then I'm going to say, look, any word for a Coxeter, any word for an element of the Coxeter group can be reduced to a minimal word. What's the length of this word? It looks very long, but the length is very short actually, because this is just si. So it looks very long, but actually this has length 1, as in terms of the generators. This big thing, this has length 1. It must, because it's equal to si. And that means that this must be equal to some subword of one letter. Yeah, I take this big long word, but really this has length 1, so I must be able to reduce it to a single letter. So what I get is si is equal to some subword of length 1, which is some s something prime. S sub something prime. And that's it, because I assumed that this is precisely what I wanted not to happen. I assumed that si was not one of the s primes. And I just proved to you that it is. That achieves my contradiction, and that shows this statement. So that's that. That shows to you that any two words, any two reduced words for W use exactly the same letters. Okay. Question?
So the S prime something is the reduced subword of that long expression?
Exactly. So let me just say that again. I have this big long expression, but this really is as an element of the group, it has length 1, because it's just si. It has length 1. And then I'm invoking this proposition that says if I have any word that is too long, then I can choose a subword that represents it and is of the correct length. The correct length is 1. So some subword of length 1 is just one of these guys, which they're all s primes. And so my si is equal to some s prime sub something. Okay. Now I'm going to show to you something that you've wanted me to show you for a long time. Proposition.
I'm sorry, Federico.
Yeah, go ahead.
I forgot already. How did you establish that these this T would be S1 through SI down to S1 is the same as S1 prime?
So your question is, how did I establish that these two sets are equal? Because of that description in my lemma over there.
Okay.
That says, basically because this set and this set, they both describe the reflections T that shorten W. And this description doesn't depend on what word I chose for it.
Right. Okay, that's right.
That's why. Okay. Proposition. You cannot write a generator in terms of the other ones. a generator of your group in terms of the other ones. Okay. This is now done, because let's see. Let's suppose that you could. Suppose that you could write S as some word S1, S2, up to SK, where these guys are in S minus little s. Okay. Well, let me just repeat my argument. Here's an element of the group. What length does it have? It looks very long, but it has length 1. And that means that by this proposition, I can shorten it to a subword of length 1. So I can shorten by deletion to equal one of the s's, which is not s, it's one of the other ones. So what I just mean, I guess I'm being a little bit sloppy. I mean s delete little s. Okay. So I just mean the other ones. I cannot write one of the generators in terms of the other ones. The reason is that if I could, I would take this expression, shorten it to the correct length, which is 1, and I would obtain an equality s equals si. So what I would obtain is that 2 of my generators are equal to each other. Now, why is that bad? Why can 2 generators not be equal to each other?
You wouldn't have a minimal selection of your generators.
But why is it that in a Coxeter group, I mean, this is something that we were worried about earlier. I define a Coxeter group by saying these are the generators, these are the relations. How do we know that it's not possible that you take some of the relations and conclude that S1 is equal to S7? Why can S1 not be equal to S7? Because of this. Because if I had 2 reduced words for an element, S1 and S3, then the set of things that I used here, S1, is equal to the set of things that I used here, S3. I couldn't have 2 generators be equal to each other because they would be reduced words that are equal, and this would tell me that that not only are the elements equal, but the letters themselves are equal. Okay. By this statement, maybe I should give these guys numbers. So this is 1, this is 2, this is 3. So I shortened using proposition 2. And then I obtain a contradiction. Using 1, sorry. And I get a contradiction using 2. Okay. So I think you'll agree with me that, I mean, this is a statement that we wanted to prove, and I told you in the forum it would take quite a bit of work to prove it. And we did it, but you should notice that really we are building on the sign permutation, because all of this stuff started with the exchange property and the deletion property, and the way that we proved these 2 properties was using this statement that really talked about the sign permutation representation. Okay. Now what I should tell you is that now we did all the hard work with the sign permutation representation, and we won't be using it very much anymore. And so far, from the things that we have done in the class, what should be most important is these two statements, because these are the ones that we are going to be using all the time. And a lot of this work on the sign permutation was a tool to get to these two statements that we'll see are extremely important. So make sure that you understand these two and you know how to use them. We need a volunteer to run the stupid questions activity on Friday. So who's my volunteer? My volunteer only needs to collect questions and then ask them here out loud.
What time?
So I sent an email to you. I hope everybody got it. I will be teaching the next 4 classes in Colombia, and you guys will be watching this here. But the first class, I won't have taught it in Colombia yet, and so for that, we're going to have an activity where you guys get to talk about the class while I'm not here, and ask each other all these questions that you might think are stupid, and you'll realize that everybody has these questions and that they're not stupid. They might be actually hard. So I want this basically for someone to moderate the discussion, but your only role is just to say, okay, question and answer during class time. Aaron will do it. So email him questions actually. A-Dal SFSU.
Lectures on our own.
Yeah, it's gonna be here.
Where is it going to be shown? In this file?
Yeah, same. So here, last time it's just that I'll be on the screen.
Wait, are you gonna be like live on the screen?
Says it is.
Yeah.
Or is it thing too slow?
That's all I did.
No, it is too slow.
You just call it my call. You probably can you take video from your iPhone?
About your comment, can I assume that we're not supposed to use the
Still playing game?
Huh?
You still playing
take
game?
care
Oh,
of
you
a couple
can
of
do
Playing games?
Really?
Game.
Then for how long?
Do you say game? You're the piano player who
Oh yeah,
plays
still
games.
playing
right?
gigs. Yeah.
Yep.
Right now we're writing new music.
So there's
Is
some
that why you didn't preview
This
yet?
is what, like the
You mentioned you can use it.
metal.
You can use it there for
Heavy metal.
Oh no, that was Chris. Chris likes
No way.
heavy metal. I was talking about my band is like multiple
Oh, I see.
not heavy metal.
No, I saw
the
this
thing
and
scan
mentioned
PDFs.
about
Scan
what
one
music you like.
Look at that. The scanner.
I guess I might have to use it.
Yeah, that was Chris. He was saying he loves heavy metal.
Yeah, it's a address book, and I'm